Okay, if this is the case, and if ultraviolet light, and you know that there's always light coming from the sun to the earth, if ultraviolet light can break these bonds, the oxygen-oxygen, and the ozone-oxygen, then why do we have any oxygen or ozone left in the atmosphere? Why wouldn't it all just be broken over time as the light just keeps coming to us, you know, for millions and millions of years from the sun? Well, that's a good question, and we aren't the first people to ask it. So scientists studied the chemical reactions. This atmospheric chemistry is very, very complicated. But one explanation for the reason why we have pretty much a constant concentration of oxygen and ozone is that the relationship between the ultraviolet light and the oxygen and ozone is a steady state reaction. That means that even though we're having chemical change, at the end of everything that's going on, you're going to have constant concentrations of your reactants and products. And this particular studying and modeling the reactions of oxygen and ozone in the atmosphere was done by somebody named Chapman, so it's called the Chapman cycle. And so basically what they said is that oxygen, you know, will absorb a UV photon. One molecule of oxygen will absorb one UV photon in the wavelength range of less than or equal to 242 nanometers. Okay, and when that happens, the oxygen is going to break into two oxygen atoms. Well, the oxygen atom, because the concentration of oxygen is pretty high, is going to react with whatever it comes in contact with. And the chances of it coming in contact with yet another oxygen atom are pretty high. So it will collide in what we call a fast reaction to form ozone. And remember, when we were talking early on about, where does ozone come from in the stratosphere, we said ozone can be formed when oxygen is in the presence of high energy. And this is how the oxygen is split apart, the individual oxygen, and then reacts with another oxygen molecule to give ozone. So in the presence of high energy, this reaction occurs. And so that gives us ozone in the stratosphere. And this is a fast reaction. It's called a collision reaction because all you have to do is have the chance of one of these oxygen atoms colliding with another oxygen molecule. Well, then the ozone will also then, when it collides with or comes in contact with the photon of ultraviolet light less than or equal to 320 nanometers, so it's a little bit a lower energy necessary to break this bond because it's a weaker bond, but then it will decay or dissociate back down to, I shouldn't say decay, I'll say dissociate back down to the oxygen atom and the oxygen molecule. This reaction actually is sort of slower, okay? Then what can happen is another path for that oxygen, or for the ozone, is that ozone can either, absorb ultraviolet light and dissociate back to oxygen and ozone, so it's a back and forth kind of a reaction, or the ozone that was just produced can collide with an oxygen atom that's produced up here to produce two molecular oxygen. Now this is also called a collision reaction because it just happens when this oxygen atom that's very reactive collides with an ozone molecule. This is a slow collision reaction because the concentration of ozone is so much lower. Now remember, the gas in the stratosphere is a very low concentration of gas. The pressure is very low, so the distance between individual gas particles is very far. So particles need to travel a great distance, or excuse me, this atom would need to travel a great distance before it would have the chance of colliding with an ozone. It'd have a better chance of colliding with oxygen because the oxygen concentration is higher up there than the ozone. That's why that's fast and that's slow. Okay, well that all looks kind of complicated, but that's how we model and explain why we just don't run out of oxygen and we just don't run out of ozone in the stratosphere as it's filtering the ultraviolet radiation that's coming all the time from the sun. So this picture here is the same thing I just described to you, but this is the picture out of your book. It's got a few more details. But sometimes when people look at these types of models of chemical reactions that are complicated, they get a bit overwhelmed and they can't deconstruct it and break it down and tell themselves a story. But if you just take your time and read it, and now you understand, what the UV photons do, what this means, that it can break the chemical bond, and then what a collision fast and a collision slow reaction means, and that this is a little sub-cycle cycling around, and you start with oxygen and you end with oxygen. That's why the whole thing is called a cycle, and you have a sub-cycle within it. But anyway, if you take your time and just read through this and study on it for 5 or 10 minutes, it'll probably start to make sense to you. And in the real world, there's a lot of chemical reactions that occur in this way. When we're first learning chemistry, we just see reactants and products and everything looks very clean. But anytime you have other types of reactants and products and just chemicals and energy around a particular chemical change, you're going to have all kinds of competing reactions and complicated reversals and equilibrium type situations. And so this is just probably the first thing like this you've ever seen. But once you get familiar with the way we diagram and the way we model and what it means physically, then these types of pictures shouldn't look so so confusing to you anymore. So this is what happens with the oxygen and ozone. This is an explanation of how the oxygen and ozone filter different energy, and it's based on the chemical bonds within oxygen versus ozone.